For the next 6 weeks, what I want to do is tell you some things about Mars that we know and some things about Mars about which we are very uncertain, with a focus on the question, is there life on Mars? Was there life on Mars? Is there life today? When I wrote this book, which is what kept me busy over the last few years, my interest was piqued because I didn't know what the answer was. I knew that NASA had been searching for life on Mars with rovers and spacecraft for the last 20-odd years, and I knew a lot of my professional astronomy colleagues had been doing projects trying to somehow discern whether life does or did exist on Mars, but I didn't know any of the details. And what I discovered in my research was that most of my colleagues actually didn't know any of the details either. I mean, the professional Martian scholars did, but no other astronomers had a clue. So this book is written for hopefully all audiences. I'm assuming that my professional colleagues might learn something from reading it, but it's written for all of you. If you want to get the book, it should exist somewhere. I don't know how you find an actual book these days. Barnes & Noble might have it. Amazon has it. But what I'm going to be doing over the next 6 weeks is going through much of what's in the book with you. And if you want to read along with me, that's fine. And if you don't, that's also fine. So let's get started. This quote from 1939 actually, I think, sums up pretty well what's going on with Mars. So much nonsense has been written about the planet that it is easy to forget that Mars is still an object of serious scientific investigation. It's hard to oversell the idea that a tremendous amount of nonsense has been written about Mars. The question, I think the big question for us is, what's the real Mars, and can we separate the Mars that astronomers and the public together have created in our imaginations over the last several hundred years from the real Mars? It's the real Mars that's actually important, but trying to figure out what the real Mars is, that's difficult. This is a general outline of where we're going. I'm going to go through the first few chapters today. Next week, we're going to focus on water on Mars, the canal controversy from a century ago, and then we're going to try to focus on what we actually know about what water does exist on Mars. The third week will be not just on lichens, but on algae and chlorophyll and other discoveries which may or may not be right about what is on Mars. October 31st, we're going to focus on the Viking mission, NASA's Viking mission from the 1970s, which may or may not have discovered evidence of life on Mars. The fifth week, we're going to talk about ALH 84001, which you will be able to say very quickly by the time we're done. Allen Hills 84001. It's a meteorite discovered in the Allen Hills region of Antarctica in 1984, which may or may not have evidence for ancient life on Mars. And then the last week, we'll talk about measurements of methane gas in the atmosphere of Mars and what that means and what the measurements actually are and whether that says anything about life on Mars. And we may or may not keep to that schedule. We'll see what happens. So let's go ahead and get started. One of the things I want to do today is introduce you to Mars. I want you to start becoming familiar with and comfortable with the idea that Mars is your next door neighbor and you should know a lot about it. So this is where we're going. Mars is a little guy compared to the Earth, but it's not that little. It bears some similarities when you just glance at it. The color seems to be different. We'll look at more of those details. Some basic facts about Mars and Earth, just again to have some numbers and ideas in your mind. The Earth is 93 million miles from the Sun. Planets orbit the Sun in elliptical paths, not circular paths, but Mars and Earth's orbits are close enough to circles. You can just think of the distance of the Earth as being the radius of a circle, and we're 93 million miles from the Sun. And I will try to use miles rather than kilometers in here. I may glitch on that a little bit. You can catch me if I'm wrong, or if I do that glitch. Mars is 50% further from the Sun. It's 142 million miles from the Sun. That has all sorts of implications for understanding Mars. If Mars is further from the Sun, it gets less light from the Sun. If it gets less light, Mars is colder. Those could be important for understanding the history of Mars. The Earth is a bigger object. In diameter, the Earth is 7,900 miles across. Mars is a little bit more than half that big, 4,200 miles in diameter. Ultimately, when you do the math and figure out spherical volumes and what the planets are made of, Mars has about 10% the mass of the Earth. So in terms of stuff, if you took 10 Marses and stuffed them together, you'd have one Earth. So the Earth is significantly bigger in mass. That has important impacts on the strength of gravity on the surface of the planet. The surface gravity of Mars is about half that of Earth, which means you could jump twice as high on Mars. That's essentially what we're talking about with gravity. But if you could jump twice as high, that also means the atmosphere of Mars is held down onto the surface only half as well, which means it's easier for gases to escape from the Martian atmosphere than from the Earth's atmosphere. That has an important effect on the history of Mars. Things that are not on here, to the best as we can tell, Mars does not have a magnetic field. Well, who cares about a magnetic field? The wind, the sun has a wind. It's called the solar wind. The solar wind is like a sandblaster on the top of an atmosphere. If a planet has a magnetic field, it can hold off the solar wind. It can protect itself from that sandblasting effect of the sun. Mars doesn't have that, which means Mars's upper atmosphere is subject to erosion from this wind from the sun. Again, an important difference in trying to understand what may or may not have happened to Mars over history. The Earth orbits the sun in 365.25 days. Who cares about the quarter day unless you're keeping the calendar? Mars orbits in 687 days, about twice as long. So the Martian year is longer than the Earth year, but not that much longer compared to Jupiter, Saturn, Uranus, Neptune, Pluto. I like Pluto. It's a planet. Okay. Mars's year is very comparable to the Earth's year. Both planets have solid surfaces. Both planets have thin atmospheres above their solid surfaces. The Earth has one big moon. Mars has two little moons. Now you know everything you need to know to participate in a Jeopardy contest on Mars. Okay? I want to talk a little bit about the formation of the sun and the planets in orbit around the sun. Not too much detail, but there's an important point I'm getting to, and that is we know something about the ages of the planets, and we also know something about when life first appeared on the Earth. And that helps us think something about Mars, because the planets appear to be so similar. So the first point is the sun and the planets formed at about the same time. The answer to when is 4.5 billion years ago, but I'll come back to that in a moment. Immanuel Kant and Pierre Laplace in the 18th century came up with our basic ideas for how planets form, and astronomers now have actually confirmed that these 300-year-old ideas are right. In interstellar space, giant clouds exist in between the stars. Those giant clouds don't just sit there doing nothing. Gravity pulls the cloud to try to make the cloud smaller. Those clouds are spinning. And as those spinning clouds are pulled together by gravity, you end up with a big, bright thing in the center and a swirling cloud, a disk, going around the thing at the center. The thing at the center is the thing that will become the star. There's a rotation axis for that whole disk, and the material in that disk, think of it like a pancake flattened around the sun. The planets form in that disk. This is the idea that Kant and Laplace put forward 200 plus years ago, and it's right. There's a telescope in Chile called ALMA, the Atacama Large Millimeter Array, and it's probably the most important telescope on the planet right now. It can see detail that no other telescope can see. This is an image. This is not a cartoon. This is not an artist's portrayal of what we think planetary formation would look like. This is a picture. This is a disk around a very young star with the fancy name HD 163296. And around that young star, there's material in this disk. And these gaps that you can see in the disk, that's where the planets are forming. In this disk, we know there are two baby planets forming in those lanes that you see carved out of the gas and dust disk that orbits the star. That's how planets form. We know that's how planets form. Planets form at the same time that the stars form. Planets are, if you will, the accidental byproducts of gravity making stars. But when gravity makes stars, it makes planets, and there are lots of planets out there. So the Earth and the Sun formed at about the same time, which means the Earth and Mars and the Sun formed at about the same time. And we know when that is, or was. The oldest meteorites that we have found, rocks that fall onto the Earth from space that have been orbiting around the Sun for a long period of time, the oldest ones are 4,560,000,000 years old. They're actually 4,562,000,000 years old. The ages are known very accurately. Those are the oldest rocks that exist in the solar system. The first solid things that formed in that disk orbiting the Sun. And as that disk evolved, some of those rocks collided together to form bigger objects, which eventually formed the planets. But some of that stuff is just debris that never formed into the planets and is still in the solar system. The oldest of those meteorites, 4.56 billion years old, that tells us when the Sun and the planets began forming. The Earth probably took another 100 million years for all those little pebbles to form boulders and rocks and moon-sized objects and accrete to form something the size of the Earth. Mars is smaller than the Earth. The reason Mars is smaller than the Earth almost certainly is because Mars is closer to Jupiter. If we go outwards from the Sun, Mercury, Venus, Earth, Mars, Jupiter, in between the orbits of Mars and Jupiter is the asteroid belt. There are no big planets there. There are no big planets in the asteroid belt because Jupiter is a bully. And Jupiter effectively acts like a stirring rod that stirs up the orbits of stuff in the asteroid belt and makes them move such that when they collide, they're more likely to splinter apart than stick together. You have to get far enough from Jupiter to get away from the bully such that you can form into bigger objects. Mars is the closest object in the solar system that we call a planet to Jupiter, but it could never get very big. Jupiter prevented Mars from getting very big. That's why Mars is different from the Earth in terms of size, but they formed at about the same time. On the Earth, we know a lot about what happened in the early history of the Earth because there are no rocks on the Earth that are significantly older than 4 billion years. The oldest rocks that exist on the Earth, I'm going to jump forward a slide and come back to this. The oldest rocks that exist on the Earth are 4,031,000,000 years old. There are mineral grains inside some younger rocks that are dated at 4.3 to 4.4 billion years old. The oldest moon rocks are in the ballpark of 4.4 billion years old, and then we know how old those oldest meteorites are. So what was going on for a few 100 million years? Astronomers, you may be getting the feeling, astronomers think millions and hundreds of millions of years are short amounts of time. So you just have to get used to that way of thinking for me. Once the Earth formed, the Earth was hot. The formation process of making a planet makes the planet very hot. And the Earth needed 500 million years to cool down. That's the reason there are almost no rocks from this early period of time. There were volcanic processes that would have formed rocks, but the rocks eroded away, or they melted away, or they got covered up. They disappeared. There's virtually no evidence of what was going on the Earth for that first 500 million years. Why are there mineral grains in rocks that are older than the oldest rocks? Sedimentary rocks form from the erosion of other rocks. You build a mountain, the mountain erodes, the grains flow into streams and rivers, they get packed onto the bottom of rivers and oceans, and they form new rocks, sedimentary rocks. Some rocks must have formed on the Earth 4.3 billion years ago, but the rocks themselves didn't survive. But individual little mineral grains that are pictured here in this bottom left picture, zircon grains. Zircon is like a diamond. It's very, very hard stuff. The zircon grains that were inside those rocks didn't disappear. The rocks in which they originally formed disappeared. So those zircon grains are now inside younger rocks, sedimentary rocks. So the rocks are 4 billion years old, but the zircon grains are 4.3 billion years old. What that means is, on the Earth, little rocks were starting to form 4.3 billion years ago, but they didn't survive. But starting around 4 billion years ago, the first rocks started to survive. Why is that important? It's important because we're talking about life. So I wanted to go backwards, and I think I did. All right. What we call the Hadean era on Earth from 4.6 to 4 billion years ago is this early hot period when nothing existed on the Earth except volcanic activity. The Archean era that lasts from 2.5 to 4 billion years ago on Earth is the era when rocks first started to appear and when life first appeared. These guys are stromatolites. This is from a place called the Hamlin Pool in Australia. They look like big lumpy rocks, but they're not rocks. These are living things. Stromatolites are layered things. Okay? The things in them are colonies of blue-green algae, which are more like bacteria than algae. They form these layers, and they grow almost like coral, layer upon layer upon layer upon layer. And they form these things that look like rocks. But these things are alive. They're colonies of blue-green algae. This is another one from the same place. There are only 3 places on Earth where these things still can grow. One of them is in Australia, and I've got a note here maybe that tells me where the others are. The other 2 are in the Bahamas, but I don't have any pictures from the Bahamas. I need to go on a field trip. Okay? These are neat things. They don't like the presence of oxygen. The Earth's early atmosphere did not have oxygen in it. You'd be very unhappy. Okay? It took life on Earth almost 2 billion years to oxygenate the atmosphere. For the first life forms on the Earth to take in carbon dioxide and put out oxygen into the atmosphere. But oxygen is very reactive. Oxygen likes to bond with other things. If you put out your potato chips, the oxygen reacts with the potato chips, and that's one of the reasons the potato chips go stale. The early oxygen that was pumped into the atmosphere reacted with the rocks and rusted the surface of the Earth. If you've heard of Red Rock Canyon and red bed formations on the Earth, those are iron oxide-rich formations that formed 3 billion years ago. When the Earth was pumping, life was pumping oxygen in the atmosphere, the oxygen was rusting the rocks. Only after all the rocks had been completely rusted could oxygen start to build up in the atmosphere. And that took almost 2 billion years. So the early Earth was very different. These creatures, these stromatolites, they don't exist in very many places anymore because they can only thrive in oxygen-poor environments. The environments that are like what they started in. When did we find the first stromatolites? The oldest stromatolites found in Australia are about 3.5 billion years old. This picture is apparently a fossil stromatolite that's been dated at 3.7 billion years old. In this picture, these red peaks that go up, those are apparently the layers, and you can see the layered structure. The layered structure of these early stromatolites. This suggests, if this is right, that stromatolites, living things, existed on the Earth 3.7 billion years ago. They certainly existed 3.5 billion years ago. This is a little less certain, but it looks pretty good to me. If that's correct, stromatolites are not simple one-celled creatures. They're colonies. They're villages, if you will. These are advanced life forms that existed when the Earth was 3.7 billion years ago, when the Earth was 800 million years old. I'm unplugged. Try again? All right. So now think about the early history of the Earth. 500 million years after the Earth formed, we could barely form any rocks because it was so hot. But another 200 or 300 million years later, we had these advanced life forms, these stromatolites. I'm not talking about intelligent life, but sophisticated life in terms of way more complex than single-celled creatures living by themselves. 200 million years later. What that suggests, if you're a biologist, is that as soon as it was possible for life to exist on Earth, life got started. It didn't take a long time once the environment of the Earth was amenable to the existence of life for life to get a foothold here. How life got started, we don't know, but once it got started, it did pretty well. 3.7 billion years ago, there was life on Earth. One of the questions for us then is, what was Mars like 3.7 billion years ago? And the answer, I'll try to convince you over the next couple weeks, is that Mars was like the Earth. 3.7 billion years ago, 4 billion years ago, Mars was wet and Mars was warm. The habitat called Mars 4 billion years ago was probably pretty indistinguishable from Earth. And if life got started that easily on Earth as soon as the rocks existed on the surface of the Earth, then life could have gotten started that quickly on Mars. That didn't mean it did, but it could have. That's where we're starting. All right. Mars. These are two different images of Mars at the time that's called opposition. Opposition is when Mars is in the opposite direction from the Sun. If Mars is in the direction of the Sun, it's up in daytime and you can't see it. But Mars and Earth orbit in different orbits, and Earth orbits faster than Mars, 365 days versus 687 days. So about every 2 years we lap Mars. And when we lap Mars, we pass it when it's on the in the opposite direction than the Sun. That time is called opposition. Oppositions occur about every 2 years, hence 2016 and 2018. These two images of Mars show that Mars looks different 2 years apart. Mars is a changing place. The environment of Mars is not stuck in place. And we want to understand some of those changes. Another thing you can pick up from these images is that, whoops, pointer. Right? There are some dark spots on Mars and some lighter spots on Mars. We need to understand what the different colorations mean for Mars. Mars has two little moons. Phobos is the big guy in front. Deimos is the little guy in back. Phobos is closer to Mars than Deimos. They were both discovered in 1877 by an American astronomer, Asaph Hall, working at the U.S. Naval Observatory in Washington, D.C. This was actually one of the seminal events getting astronomy started in the United States, the discovery of these two moons. This is a close-up of Phobos. It's an odd little guy, 17 by 14 by 11 miles. It's lumpy. It's not spherical. Let's segue to Pluto a moment. One of the arguments for distinguishing between a planet and something that's not a planet is that a planet is massive enough that its gravity squishes it into a spherical shape. Phobos is not big enough to do that. An object probably has to be 300 or so miles across to have enough mass, to have enough gravity to do that. Pluto's big enough to do that. Pluto's a spherical object. One of the reasons why a lot of us think Pluto merits being called a planet. Phobos doesn't. Phobos is just a lumpy potato-like thing. It orbits Mars in 8 hours. That's a really odd thing to do because Mars spins in 24 hours, as we'll see in 15 minutes when we get to that data point. But Mars does spin in about 24 hours. If you have a moon, if a planet has a moon that orbits faster than the planet spins, the tides, the tidal interaction between the moon and the planet actually drag the moon down. The Earth is pushing our moon away. It moves away a few millimeters a year, so the moon is getting steadily further away from us. We know this because we put mirrors on the moon in 1969, and we can bounce lasers off those mirrors and very accurately measure the distance to the moon. And the moon is spiraling away from the Earth, slowly but surely, just as is predicted from our understanding of how tides work. The tides are doing the opposite thing to Phobos. They're dragging Phobos down. So in about 50 million years, blink of the eye, Phobos is going to either disintegrate and get torn apart by the tides, or it's going to crash into the surface of Mars and not be there any longer. What that tells us is that Phobos has not been in orbit around Mars for a long time, astronomically speaking. It may have been in orbit around Mars for 1 billion years, but probably not for 4.5 billion years, because it can't start infinitely far away and spiral in. There's an outer limit to how far it can be and then spiral in. So it hasn't been spiraling in for the lifetime of Mars. It's probably a captured object, an object that was in the asteroid belt and came close enough to Mars that Mars was able to capture it. our moon has been part of the Earth-Moon system since the Earth formed. Oh, I wanted to point out to you in this picture, in the lower right here, if you can kind of figure out the topography, there's a giant crater called Stickney. Something must have hit Phobos to create that crater, and the stuff flew off into space and left behind the crater. Phobos is an interesting object. This is the other side of Phobos. It doesn't have a big crater, but it's got lots of craters. It also has these interesting striations that I don't think we understand. But the craters come from impacts, and the more craters it has, the longer it's been sitting there getting bombarded by things from space. Phobos doesn't seem to be that old an object. So more information on that. Deimos. Deimos is the other moon. We don't have as good images of Deimos. It's little. It's about the size of Nashville, 5 by 3 by 3 miles. It orbits in 30 hours, so it orbits in a longer period of time than Mars spins, which means it's spiraling outwards away. These are a whole bunch of different images of Deimos. I wanted to show them to you just so you get a feel for what little objects look like. They're lumpy, they're funny shaped, they're not spherical objects like planets. And now back to Mars. Let's meet Mars. Mars has this spot at the top, which is the northern polar cap. You don't see it at the bottom, but there is a southern polar cap, although not in this picture. Over here is a big volcano called Olympus Mons, and there are 3 volcanoes here that are on this part of the planet. This part of the planet is lifted up. It's called the Tharsis Bulge. Those are the 4 big volcanoes on the surface of Mars. You should start getting familiar with some of these objects on Mars just as you're familiar with Asia and Antarctica and Australia. Here we have Olympus Mons, so we've got a close-up of that Tharsis Bulge region. Now these 3 volcanoes get names, none of which I can pronounce, but they're all big volcanoes. They are more like the Hawaiian Island volcanoes than they are like volcanoes in the Pacific Northwest. They don't come from the subduction of plates on the planet that then melt and produce the volcanoes. These are hot spots. They're places where hot stuff has been coming out of the planet continually. These volcanoes are enormous, much bigger than any volcanoes on Earth, because they've just been sitting there forever growing. Olympus Mons does not appear to be dormant. It may not have erupted for the last 50 or 100 million years, but it doesn't seem to have stopped doing whatever it's doing. So something is going on inside Mars which can still produce some heat. This is another view of Olympus Mons. It is a big lump on the surface of the planet. And this is a close-up. The peak of Olympus Mons is 70,000 feet. That's a whole lot of miles. I don't know what it is, 22 miles, something like that. The base is almost 400 miles across. So the base, the mountain, Olympus Mons, if you set it down on the state of Missouri or the state of Nevada, it will basically cover the whole state. These are big objects, and it might be active. At the very top, you see this crater. That crater is not an impact crater. That's the volcanic caldera at the top, which has not been completely eroded by impact craters hitting it, which also tells you something about how young the object is. Another important feature on Mars is called Valles Marineris. It's this crack that goes across the planet. Valles Marineris is a big crack. This is a focused image on it. It's about 2,000 miles across. It's about 5 miles deep on average, which means it would stretch across most of the United States. It's a big, big crack. This is not the Grand Canyon. This is something very different from that. It's probably because the heat from inside Mars expanded the planet and just cracked it open. So if you took the skin of an orange and squeezed it and it just popped apart, that's probably what's going on with Valles Marineris. This is just a neat impact crater, which is at one end of Valles Marineris. If you look at it carefully, this edge here goes up. The topography goes up. This is the rim of the crater. And then you see the inside of the crater here. Just a neat feature. I want you to see some close-ups of Mars because we really know a lot about Mars. We know Mars in great detail. Syrtis Major is this dark feature here. Syrtis Major is one of the very first things that astronomers noticed on the surface of Mars. It's a dark patch that doesn't go away. This is a close-up of Syrtis Major. You can see in these images, if you look closely, there are impact craters everywhere. Impact craters have these raised little mountains at the center of them. They're all circular. In some places, you see an impact crater with little impact craters on the rim of the crater. Again, counting the craters helps you date how old the surface is. Syrtis Major doesn't have as many impact craters, at least visible, as outside of Syrtis Major. So there's something going on that's slowly covering up the craters, or at least making them harder to see. At the right edge of Syrtis Major is this smooth area. If you look carefully at this smooth area, you don't see any of these intermediate and big-sized craters. You just see little craters, which means that surface is younger. Something happened to pour some lava out into that area to smooth it out or to erode it, and it has had less time to collect craters. That region that's so smooth, here's Syrtis Major. And again, in this image, you can see better the lack of craters in Syrtis Major. And this region over here is known as Syrtis Planitia. And up to the right of that is Utopia Planitia. The plains are these flat, low-lying areas. The reason they're colored blue is because you have a bias when you look at maps of the Earth to think that topographically low-level regions have water in them. The oceans have water because they're low. That's where the water goes. Water runs downstream and downriver and goes into the Gulf of Mexico. Then it comes out in hurricanes and hits Florida. Okay? But low-lying regions on Earth are blue. So the NASA folks have colored in the low-lying regions in some of these images of Mars just to fool your brain into recognizing their low-lying regions, their low-elevation regions. There's no water in them, but there could have been. Syrtis Planitia itself is probably, it's relatively round, it's probably an old impact crater, a very old impact crater that created this low elevation region, which means once upon a time in ancient Martian history, if, big if, but if Mars had lots of liquid water on the surface, this could have been a giant reservoir of water, a giant Lake Michigan, a giant Gulf of Mexico, a large volume of water. And if you wanted to search for life on Mars, follow the water. Follow the clues as to where the water is or was, because those would be the most hospitable places in ancient times for water to exist. The northern polar cap. The northern polar cap is about 700 miles across. It's a fairly big polar cap. It's smaller than the Earth's polar caps, but it's a polar cap. This is a close-up to try to see some of the structure in the northern polar cap. It's got these wonderful spiral-ish features, and it's got this enormous crack, which gets its own name, Chasma Boreal. Chasma Boreal is actually the size of the Grand Canyon, unlike Valles Marineris, which is much bigger. So in the northern polar cap, there is this giant crack, which may or may not be some kind of erosion feature, but it's big and it's there. This is a topographic image where you can start to see some of the structure in that map. You'll also notice in this particular image, there's less ice than in this image. What happens in the polar regions is that you have a veneer of carbon dioxide ice, dry ice, and in the summer for that hemisphere, the CO2 ice sublimates, and you can see below it, and you start to see the exposed water ice. Most of what you're seeing in these polar caps is the top layer of dry ice. This is another image of the edge of the polar cap. You can see there's the steep cliff of ice going down. You can see the layers of ice that form year after year after year. A lot of similarities to Earth, one of them being this polar cap exists. These are sand dunes in the northern regions, not in the polar cap per se, but near the polar cap. You can actually see water here, ice in the edges of some of these regions, dry ice. In the summer, that dry ice sublimates and is not there anymore, but we can start to see these seasonal patterns taking place on the surface of Mars. One of the reasons I wanted to show you this and some of the other pictures that you're about to see is I want you to understand just how much detail we have in looking at the surface of Mars. We actually can see more about the surface of Mars now than about the surface of the Earth, because 75% of the Earth is covered with ocean, and it's really hard to study the bottom of the ocean. Mars doesn't have that problem. In this image, this block right here, there are a bunch of these blocks. These are icebergs, chunks of ice that have fallen off the cliffs. And in different images of these same regions, we can see before and after that block wasn't there, and then the block was there. We can see, again, these processes at work on Mars. Mars is not a dead planet. Geologically, Mars is active. Things are happening on Mars. 3 different images of the northern polar cap. These are from 20 years ago, 96, 97, January 97, and March 97. And you can see this top left, the polar cap was at its largest extent. And a year later, or 9 months later, it's much smaller. Much of the ice cap disappears in the summer, and then it comes back in the winter. These images are from the Hubble Space Telescope. This is the southern polar cap. It actually doesn't look much different from the northern polar cap. The difference is there's more ice in the north than in the south. This polar cap is just shy of 300 miles across, but the same phenomena apply. This is a map showing the different ices in the polar cap. The kind of tan areas point you at water ice, which is overlain by the dry ice. And it's the dry ice, again, which disappears in the summer, leaving behind the water ice. And I see my words got... All right, what do we do? All right, don't know what happened. All right. This, again, is in the South Polar region, and I'm sorry that the words are cut off, but there's this nice hole or crater. We don't know if it's a collapsed crater or an impact crater, but something happened. It looks like the ground just sagged like a pothole in the road. But you get this Swiss cheese type of structure as the CO2 ice sublimates away. You also get this weird kind of feature. They're known as spiders, this spider web, spider leggy features. These are caused by erosion by the CO2. As the CO2 warms up, it turns into gas, and it actually almost bubbles underneath uphill and causes these erosion features. Each of these lines that you see is about half a kilometer in width, 500 meters wide. They're not very deep, but they're very wide. And one other odd-shaped feature near the South Pole, these look like hieroglyphics carved into the walls of caves. But these, again, represent the erosion patterns, the evaporation patterns of ice as the dry ice, as the CO2 ice sublimates away. I just like this picture. All right. Let's go to Mars. Sunset. We're on Mars. Human beings with legs are not on Mars, but we have a presence on Mars. We can watch the sunrise and the sunset with our robots that are on Mars. This is an image of the sunset on Mars taken by the Curiosity rover. The Curiosity rover is in a place called the Gale crater on Mars, so all of that's in that figure caption. The Curiosity rover, its main job is to study the Gale crater because we thought the Gale crater was a place that might tell us a lot about life on Mars or ancient life on Mars because it looks like there were ancient lakes in that crater. And the evidence from Curiosity seems to have confirmed that, which probably means future missions will also go to study the Gale crater, which means you should know what the Gale crater is and what's going on with the Gale crater. Among other things, it produces nice sunsets. This is another image from the Curiosity rover. This mountain in the background is known as Mount Sharp. You can tell from the colors Mars looks like a red desert because it is. Another view from the Curiosity toward a ridge of mountains known as the Vera Rubin Ridge. A lot of words on this slide, but you don't have to read them. There are different geological features you can see. You can see in the back here, there's this kind of whitish region in between, a darker region. Up close, there's this spiky, lumpy region. There are clearly different rock formations and mineral species on the surface of Mars, and we can identify them by looking at these images. Yes, sir.
Why did they name that area after
Vera Rubin? Why did they name that after Vera Rubin? I think because they wanted to. Vera Rubin is a very famous, now late astrophysicist who discovered much of the evidence for what's called dark matter in the universe. Vera Rubin should have won a Nobel Prize. The Nobel Prize Committee, I think, has tended to shy away from astrophysics discoveries for Nobel Prizes, though they've given out some. They've also been hesitant, shall we say, to give out Nobel Prizes to female physicists. So instead, she gets a mountain on Mars. There are naming protocols for features on other planets. I can't simply name something on Mars, but the folks on the Curiosity mission team that discover different features that they would like to name, they can propose names for those features like Mount Sharp, and the International Astronomical Union then has to approve the namings. Why they came up with Vera Rubin Ridge, I don't know, but I like it. Yeah. These are some close-ups. These are, you can see the sand on the surface. You can see the eroded sedimentary rocks on the surface. To have a sedimentary rock means you had to have water. You had to have a liquid environment to collect those sediments. This picture, almost more than anything else I could show you, says to you Mars was wet for a long time, long enough to form these sedimentary rocks. Now, we don't have any kind of radioactive dating on these rocks yet to know when they formed, but I would sure love to see that happen. These are sand dunes. You can see the ridges on the sand dunes. Mars has a lot of wind that slowly sculpts the surface and moves this sand around, and the sand is very iron-rich, which is what gives Mars its red color. For some scale, in the middle of this picture here, that's a meteorite. It's an iron-nickel meteorite. It's about the size of a golf ball. This is a close-up of stuff on the surface of Mars, and I like this picture. This is not a natural formation on Mars. This is actually a drill hole. The Curiosity rover has a drill, and the circumference of that thing is about the size of a dime, and it has drilled into this rock to try to see what's down there. Curiosity can't drill very deep, but future missions will be capable of drilling much, much deeper. It depends on how far in the future you want to go to try to speculate about that, but it's easy to imagine us sending the equivalent of deep-sea drilling rigs to Mars to drill down a kilometer if that's what we wanted to do. This is a nice little hill. It says it's 16 foot tall. Again, sand, wind-blown sand covering up whatever this rock is. And now I just have some pictures that I think are really pretty. What you have in the main part of the thing, you have what looks like an old crater, but it's probably not. This is probably bedrock, probably some sort of rock formation rather than a crater formation, even though it's relatively round. And then you have some covered up stuff. It looks kind of greenish. It's not moss. It's not algae. It's not alive, but it's pretty. These are some other sand dunes. This is inside a crater known as the Leo crater. And again, you just have this really beautiful feature here. Artists, I don't think, could have done this. Nature did it. This is, you can see the layers here of the bedrock, and you can see the wind-blown sand sediments here. Similar thing here, but these ripple lines are not sand. This is rock. These ripple lines probably are exactly that. They are from water flowing down an ancient river, leaving layers behind that form sedimentary rocks, and you can see the ancient evidence of water flowing on the surface of Mars. These have nothing to do with water, but you can see these lines in the rock. I don't have any elevation information about these, but almost certainly these formations, these structures are the result of tectonics, not necessarily plate tectonics, but the expanding and contracting of the crust because of heat trying to get out of Mars. This is another unnatural formation. This is the track in the sand behind the rover wheel from the Curiosity rover. It helps you see what's really going on there. I think the rover has nice wheels to get across the sand. If you were to go to Mars, I don't know whether you'd need the equivalent of snow boots or something else, but much of the surface has this soft, powdery sand everywhere. This is another feature that shows some evidence of water. It's referred to as a tadpole crater. Pretty obvious. This is an old impact crater that almost certainly was once filled with water, and then the dam broke. Something happened and the water flowed out. That's the tail of the tadpole. In order for that water to flow out like that and cause that feature, either it had to be catastrophic, such that the water flowed at such a rate it could rip the rock apart, or it had to be flowing for a long, long period of time in order to erode that feature. We don't have any knowledge of how it would have formed. This is known as the Ladon Basin. This looks like very, very old stuff. This is an old impact crater on which lots of stuff has happened. I have no idea what all the things are that have happened over billions of years of history to fill and change that crater, but this feature is billions of years old. No evidence of water in this particular region. All right, now we're going to switch gears a little bit. I want to introduce you to your friends and neighbors on Mars. The InSight mission is a NASA mission that was launched on the 5th of May of this year. It's due to land on Mars the Monday after Thanksgiving, November 26th. So that's your first homework assignment, to put that on your calendar so you can watch for that landing. InSight stands for Interior Exploration Using Seismic Investigations, Geodesy, and Heat Transport. And if you think NASA doesn't have people working full-time to come up with acronyms, you're fooling yourself. That's an impressive one. InSight will have a seismometer on it, which means it's trying to measure Mars quakes, among other things. Landing on Mars in just a month and a half. The most recent object to get to Mars is the ExoMars Trace Gas Orbiter. This is an ESA mission, a European Space Agency mission, rather than a NASA mission. It was launched in 2016 and landed in October 2016. You can start to get a feel for these dates. March to October, 6 to 7 months. For the InSight, May to November, 6 months. It takes 6 to 7 months to get to Mars from when you launch something from Earth. The best launch windows will get you to Mars 6 or 7 months later. The ExoMars orbiter is designed to try to measure gases in the atmosphere. MAVEN is a NASA mission, an orbiter mission also. MAVEN was launched in November of 2013, got there almost a year later, September of 2014. MAVEN is the Mars Atmosphere and Volatile Evolution mission. MAVEN is trying to measure how quickly gases erode from the top of Mars's atmosphere, which, if you run the movie backwards, can tell you something about what was there in the past. What's known as MOM, the Mars Orbiter mission, is actually a mission from the nation of India. It's their first mission to another world. I think they also have a mission to the moon right now. The Mars Orbiter mission is most important just because it's India's first interplanetary spacecraft. It's a little guy. It's got a few instruments, a very small payload. I don't know of any significant science that has come from it yet, but it's there. The Curiosity rover, which I've mentioned a few times already, it was launched in November 2011, got to Mars August of 2012. Curiosity is a rover. It's about the size of a big dune buggy, and it is in Gale Crater trying to detect evidence of sedimentary rocks, of ancient organic life. It has not found life, but it has found some interesting pieces of evidence suggesting that life could have been there. The Mars Reconnaissance Orbiter was launched in 2005, and it's still active 12 years later. The Reconnaissance Orbiter's job was mostly to search for evidence of water using cameras and spectrometers to try to look at the surface and see whether anything on the surface looks like it does or did have water there. The rover Opportunity was sent in 2003. It was active until about a month ago. Then a big dust storm hit Mars, and at the moment the dust storm seems to have knocked it out. It may simply be that the solar panels need time to recharge, but we have lost touch with the Opportunity rover for the first time in 15 years. But it was active for 15 years and might come back, but at the moment we can't talk to it. Mars Express was launched also in 2003. This is another European Space Agency mission. Mars Express was mostly a pioneering mission for the European Space Agency to show that they could successfully get something to Mars and do something. The Mars Express actually had two components, an orbiter and a lander. The lander was called the Beagle. The Beagle actually crashed into the surface, so it didn't land very well. But Mars Express is still doing very well. And then we have the Mars Odyssey, which is the oldest active mission. The Mars Odyssey is a NASA mission in orbit around Mars. Started in 2001. I lost count of how many missions that was. We have a lot of eyes and ears on Mars. Some of them physically on Mars. We have 2 rovers, one of which may not be active anymore, on the surface. And we have a half dozen orbiters watching the surface of Mars, watching the atmosphere of Mars, trying to understand Mars. Going forward, we got some other stuff. The ExoMars rover is a European Space Agency mission that is scheduled for a 2020 launch. The ExoMars rover is tasked specifically to look for evidence of life. NASA has its own rover just called Mars 2020 rover. I think they may have a contest to give it a name, but it doesn't have a name yet. What's the 2020 Mars rover supposed to do? Look for evidence of life. All right. Someone else in the news. All right. All of that information from missions, the InSight mission, the European rover that's going, the NASA rover that's going, we're still sending stuff to Mars. And every 2 years we send more stuff to Mars. And we have all these orbiters on Mars, and we have these rovers on Mars. Mars is an incredibly well-studied place at this point in time. What we know about Mars now is that we want to know a lot more about Mars. Okay. What next? All right, Elon Musk and SpaceX. Elon Musk wants to go to Mars. Let's forget all about the whole Tesla business and just focus on SpaceX, okay? Elon Musk wants to go to Mars. Elon Musk has said many times in many places that the reason he developed the idea for SpaceX is he wants to send humans to Mars. Can he do it? I think the answer is yes. So let me show you what just a few of the things SpaceX has done this year. On May 5th, this is the re-entry of the Dragon rocket supply ship that took supplies to the space station, the International Space Station. The main way in which we resupply the space station now is through SpaceX missions. May 22nd, SpaceX launched this rocket from Vandenberg Air Force Base in California. This one had 7 different satellites on board that it then deployed once it was in orbit. 5 of them are Iridium satellites, whatever those are, and 2 of them are called Grace FO satellites. I have no idea what those are. But SpaceX is now the major player in launching satellites into Earth orbit for companies. NASA has effectively outsourced the launching of satellites to SpaceX. August 7th, the Falcon 9 launched from Florida, from Cape Canaveral, with a telecommunications satellite for Indonesia. September 10th, they had a launch, I don't know where from, but either Vandenberg or Cape Canaveral, of another satellite, a telecommunications satellite. October 7th, another launch, this one just 3 days ago from California. This was all over the news because it was such a spectacular nighttime launch from California. Another, whatever SAOCOM-1A satellite is, I assume it's telecommunications, it doesn't really matter. They're in the business of launching satellites, and they're doing it several times a month. Dozens of launches per year. That's what SpaceX is doing now. They are in the business of rockets, and they're good at it. The rocket that launched for the first time this year on March 10th is this guy. It's called the Falcon Heavy. Most of the other rockets you see are known as the Falcon. The Falcon Heavy is bigger. The Falcon Heavy was a very successful launch in March. What was he doing with it? Well, SpaceX had a payload of a Tesla in the Falcon Heavy, and that Tesla is on its way to Mars. The Falcon is capable of putting things into Earth orbit. You can dress them up, but you can't get them to wear one of these things. All right. The Falcon Heavy is capable of going to Mars. It's taking a small payload. The Tesla is a couple thousand pounds, but it's a payload that's going to Mars. It's not capable of going into orbit around Mars. It's going to fly right past Mars and take that Tesla deeper into space. But the Falcon Heavy worked. And the Falcon Heavy is capable of getting beyond the Earth out into interplanetary space. SpaceX can do that. What's next? SpaceX has plans for a rocket that they'd been calling the BFR for quite a while. If we're polite, we use their name and call it the Big Falcon rocket. Okay? So that's the BFR. The BFR was also in the news last month because, though the BFR does not exist yet, the first humans who will travel on the BFR do exist. A Japanese artist, I guess, Yusaka Maezawa, I don't know how to say that right, but he has paid a whole lot of money, I don't know how much money, to be the first traveler on the BFR on a flight that will take him to the moon and back. Not to land on the moon, but out to the moon, and orbit around the moon, and then back. The money that SpaceX is getting by agreeing to send this gentleman to the moon will help pay for the development of the BFR. This announcement last month was the first glitch that I noticed in the SpaceX program. Elon Musk made announcements in 2012 and 13 and 14 and 15 and 16 about what they're doing next year. And they had announced a while ago that in early 2018 they would have that first launch of the Falcon Heavy. And they did it, and it works. He has kept to his schedule. And for quite a while, he's been saying that the BFR would have its first launch in 2020. And by 2022, the BFR would be capable of taking payloads to Mars and dropping payloads onto the surface of Mars, and that he would send dozens of BFR launches to Mars in order to supply Mars ahead of a planned 2024 launch of humans on the BFR to Mars. that in 2024 he planned to put colonists on the surface of Mars. Since the BFR now, we're told, is only going to be ready maybe to take this guy to the moon in 2023, I think the 2024 colonists to Mars date has slipped, but that's the first time any of his planned launches for SpaceX have slipped. And the BFR is a big, tough project to get going. The reason to talk about all the SpaceX stuff is I want you to believe, I want you to be convinced that going to Mars is a very real possibility very soon. It's not obviously going to happen in 2024, as Musk has been saying for a few years, but it could happen in the 2020s. It could happen by 10 years from now. We could have humans on the surface of Mars in 2028. I think that is realistic. Might not happen, but it's realistic. If someone had told you 10 years ago that humans would be on the surface of Mars in the 2020s, I think we would have all laughed at you, because NASA's not going to make that happen. But Elon Musk might make that happen. Now, there's something else you should understand about the whole BFR rocket business in going to Mars, and that is it's a one-way trip. There are a lot of people, I think, who would be very happy volunteering to go to Mars. I think Elon Musk will have no end of people who are willing to go to Mars on a one-way trip, with the promise that SpaceX will do their best to try to keep him alive. They'll try to keep him alive on the trip to Mars, which they can't guarantee right now they can do, because interplanetary space is a very harsh environment. You've got ultraviolet light, you've got X-rays from the sun, you've got cosmic ray particles. The chances of being protected in that BFR all the way to Mars on that 6 or 7 month journey and not developing cancer and dying is small. But they might make it. Maybe by the time they launch it, they'll have ways to protect the astronauts from that dangerous radiation. But at the moment, they don't. But assuming they get to Mars, assuming they land safely on Mars, assuming they can grow potatoes on Mars, right? Matt Damon style, assuming they can find water on Mars, they're on Mars. BFR can't bring them home. In order to come home from Mars, assuming you've landed on Mars, that rocket that has to blast off the Earth, go back and think about this rocket again, that rocket is mostly fuel tanks. You need all that fuel to get off the Earth. The surface gravity of Mars is only half the surface gravity of the Earth, which means you only need half that much fuel. But you need that much fuel to land safely on Mars, otherwise you crash and burn. So you need to take a lot of fuel with you to carefully figure out how to land safely on Mars, and then you need to take all that fuel with you to get back off of Mars. And in order to take all that fuel, you need a much bigger rocket, because you've got to have enough fuel to get off the Earth, not only to get off the Earth, but to take all that fuel with you, and most of the rocket's fuel. You can't do that, which means you've got to grow the fuel or manufacture the fuel on Mars if you want to come home, and no one knows how to do that. So these first colonists to Mars, who may go within a decade, may or may not come home. Elon Musk is not the only player in this game. Jeff Bezos has his own rocket company, Blue Origin. How many of you made Jeff Bezos richer this morning by buying something from Amazon? You know, a few of you, right? Well, you are funding Blue Origin, among other things. Bezos is not as far along with his rockets, but he has one rocket called New Shepard, which is in development, and they've done some test launches of New Shepard. The plan for New Shepard is not to take people to Mars. Bezos' first plans is to put people in Earth orbit, and first the New Shepard, and this is words from his website, want to know where you can buy tickets. Okay? He is going to make money from people paying to go 100 miles above the surface of the Earth in the New Shepard rocket. The next rocket he has is the New Glenn rocket. The New Glenn rocket will be bigger, and it doesn't exist yet, but you can see on the right here a couple of the so-called New Glenn rockets that are imagined, and they're compared here in the middle. There's the Falcon Heavy. So these are big guys. The New Glenn is supposed to put as many as 1 million people, a couple at a time probably, but 1 million people into Earth orbit. Jeff Bezos has this dream of putting millions of humans to work in Earth orbit. I don't know what they're going to be doing. I'm not sure that's how you make Amazon deliveries. But manufacturing, I don't know what else will be done, but his vision is that humans will live in space, in Earth orbit, and he will put millions of us up there. He does also plan to go to Mars, but that's a longer-term commitment for Bezos. NASA plans to go to Mars. This is from NASA's website. You don't have to read all the little pieces of it. It's just an illustration of NASA at work going to Mars. NASA's plans for Mars at the moment include a trip in the 2030s, probably in the late 2030s, but a trip in the 2030s to the Mars system. NASA is not currently talking about putting astronauts on the surface of Mars. Why not? Because NASA can't get them back off the surface and bring them home. And NASA, because they're using your dollars to pay for the trip, I think has an obligation to be able to bring our astronauts home alive. Elon Musk, it's a private enterprise. He can do whatever he wants. And if individuals want to go to Mars and die, they can do that. But NASA, I think, can't do that. So NASA is not going to put astronauts on the surface of Mars until we can also bring them home, or hope to bring them home. So NASA's plan is a trip to the Mars system, as opposed to putting footprints on the surface of Mars. They're not the only players. The United Arab Emirates has a plan they call Mars 2117. The United Arab Emirates does not have rockets. They don't have a space agency, but they do have money and deep pockets, and this is their imaginary city that they plan to build on Mars, a city on Mars by 2117. Can they do it? I don't know. But at this point, I think you have to say it's possible. And the last announced player in this game is called Mars One. Mars One is a private group out of the Netherlands. They, again, don't have rockets. They intend to buy the components they need off the shelf. They're going to go to Costco and pick up a rocket to Mars and a habitat. But they have plans. They have investors who think this is possible. They have picked astronauts who are in training to go to Mars. Don't know how they're going to get there, but this is possible. At least 5 different groups right now are planning to go to Mars. You should walk out of here believing that, if not in your lifetime, in your children's lifetimes, we are going to Mars. Unless somehow we put the brakes on this idea, humans are going to Mars. We will be a multi-planet species by the end of the 21st century, unless something changes what we're trying to do. Mars is this close, literally and figuratively. Getting to Mars, we are very, very close. Let's do some astronomy. Here's Mars. Doesn't look like much. If you have a nice little telescope, you'd see Mars look like a nice fuzzy little dot. If you had a better telescope, you might be able to pick out that Mars is the good-looking guy down here. This is Saturn. The little dot at 2 o'clock is Saturn's moon Titan. This blob down here is a star cluster known as M22. Planets look different from other objects in the sky. And from the very first moments when telescopes were invented 400 years ago, astronomers started poking at planets because they were more interesting to look at than stars, because stars are just little points of light. And as we've seen with Mars, Mars has colors, Mars changes, though it took astronomers a while to start figuring out what the deal was with Mars. Christian Huygens was the first astronomer to do something important in observing Mars. In 1659, he pointed his little telescope that you can see at Mars, and he got this wonderful picture. Now, a picture is a stretch. It's a sketch. There were no iPhones to take pictures. There were no digital cameras to take pictures. You looked with your eyeball, and then you drew a sketch. This is his sketch of Mars. The first thing he saw is that there are dark patches and lighter patches on Mars. We've confirmed that, right? But this is the first discovery that Mars was just not a little blob of redness, but there were dark patches and light patches. He then studied Mars night after night, hour after hour, and what he discovered is that this dark patch moved. If you watch it, a few hours later, the dark patch is over near the edge. And then it disappears. And then it comes back on the other side, and then it comes across the middle. Mars rotates. And he measured the rotation period of Mars, and my time is up, but I'm going to finish this slide. Okay. Thank you. Okay. He measured the rotation period of Mars and discovered it was 24 hours. He was very close to having the right answer. 24 hours. The very first measurement of Mars, forget all the modern stuff we know about, the very first measurement of Mars said to astronomers, Mars is just like the Earth. It rotates in 24 hours. That's the first message we had about Mars. Where we're going with this next week is measurements that show how much more like the Earth Mars is. The conclusion that Mars is Earth-like is a reasonable conclusion. And this is the first piece of evidence that says Mars is like the Earth. And if Mars is like the Earth, we're all here, okay, then could Mars have life? That becomes the big question for astronomers. So we've set the table for where we're going. The question is, what is Mars really like? What have astronomers measured on Mars that tells us something about life on Mars? So thanks for being here. Thanks for most of you staying awake. Thanks. Questions?